Hi, I'm Kai. Now I'm going to do the question 1 of homework 11 for probability and stochastic processes. So the question 1, we have a stochastic process x of t, and it is a real Weiss stationary process and with autocorrelation r of tau and power spectral density s of tau. And we need to show the r of tau is real and even, and s of tau is even and non-negative. So at first, we show r of tau is real. So we know by the definition, the autocorrelation r of tau is equal to the expected value of x of t plus tau times the conjugate of x of t. And we know x of t is real, so the conjugate of x of t is equal to x of t. So the this expected value e of x of t plus tau times x of t is real. So r of tau is real. And next, we show the r of tau is even. And from the above equation, we know RSS of tau is equal to E of x of t plus tau times x of t, and this is RSS of t and t plus tau. And we can change them, so it will become E of x of t times x of t plus tau, and this expected value is equal to RSS of t and t plus tau, and this is equal to RSS of minus tau. So now we show the RSS of tau is equal to RSS of minus tau. So RSS of tau is even. And next, we show the power spectral density S of omega is even. We know by the definition, the power spectral density S of minus tau is equal to the Fourier transform of the autocorrelation R of tau. So it is equal to the integral tau from minus infinity to infinity, and r ss of tau times e to the power of j times omega times tau d tau. And then we let lambda is equal to minus tau. So this integral will be minus lambda grows from infinity to negative infinity, ss of minus lambda times e to the power of minus j times omega times lambda d lambda. And then we can remove this negative and swap the lower bound and upper bound, and it will become the integral lambda goes from minus infinity to infinity, ss of minus lambda times e to the power of minus j times omega times lambda d lambda. So from the above, we know the autocorrelation RSS is even. So the RSS of minus lambda is equal to the RXX of lambda. So this integral is the Fourier transform of sxx of omega. So now we can see the sxx of minus omega is equal to sxx of omega. So the power spectral density S of omega is even. And next, we show sxx omega is non-negative. We can use we can discuss example of linear systems. So in this linear system, the input is the y stationary s of t, and the system function is h of omega, and the output is y of t. And the energy spectrum of the system is equal to 2 pi times the delta of omega times omega minus omega 0. And now we compute the expected value of the absolute value of y of t squared, and it is equal to 1/2 pi times the integral. Omega goes from negative infinity to infinity. The energy spectrum times the sxx of omega d omega. And we know this energy spectrum is equal to 2 pi times delta of omega minus omega 0. So we can take this 2 pi out, and it is equal to 1, and this integral will equal to sxx of omega 0. So now we can see that any value of sx of omega can be viewed as the second moment of the process y of t, that is e of the absolute value of y of t squared. So we know this second moment of the process y of t is larger than or equal to 0. So the sxx of omega is also larger than or equal to 0. So it is non-negative.